Hello, ladies and gentlemen. I would like to welcome you to the colloquium at TU Dortmund University. Our speaker today is Professor Dr. Matthias Schneider from the Faculty of Physics here at our university, and he is going to talk about we can still stop Corona. He published an article in the newspaper Die Zeit in Germany, which was very well received. And so it is, of course, clear that this is a very interesting colloquium talk. Before he starts his talk, I would like to take the opportunity to introduce him. I have to switch back to the presentation. And you see here his CV in German, but I'm going to translate it. He got his PhD at the Technical University in Munich in the year 2003, before he got the diploma in physics at Göttingen University in the year 1999. Then he moved to Augsburg, to the University of Augsburg, from 2003 to 2009, where he got his habilitation in the field of physics. He was guest professor in the year 2008 at the MIT, and from 2009 to 2015 he was professor for biological physics at Boston University. And since September 2015 he is professor here at TU Dortmund University, professor for medical and biological physics, and he is also responsible at our place for the field of medical physics, the study field of medical physics for our students. He got particular awards during his career so far, the Innovation Award of the Federal Government of Germany in the year 2007, an ERC starting grant in the year 2009. In the year 2014, the Baxter Bioscience Award and the Pfizer Award in the year 2015. His major topics are the physics of living systems, signal transmission in biological cells and biological interfaces in general. And he told me that, of course, COVID-19 is not his major topic. It's more or less his hobby, but it's still physics. It's the hardcore of it is physics, and so I told him it would be very nice to give a talk in our physics colloquium, and so he did. So I hope you will enjoy the talk, and Matthias, please start.
Yeah, ladies and gentlemen, we wouldn't need to be here. And I don't mean me here in this lecture hall and you at home in front of your computers, but I mean the society in the situation we are in. Because one thing seems to be crystal clear. If you want to stop a fire, you do it when it's small. You do it when it's little, not when the whole city is in flames. You don't need a PhD in physics to know this. You don't need a PhD in medicine or in economy to understand that. And in principle, this was part of the message from Yanir Bayam, a theoretical physics professor from Boston, who studies outbreaks since 15 years and also advised the WHO during the last Ebola outbreak in West Africa, and Nassim Taleb, a very charismatic scientist from New York who deals with risk and probability theory. This was a little confession that I wanted to give so you know where I stand. A second confession that I want to make is that this tonight is not a technical talk about a physical perspective on all this. It's an attempt to try to understand or to explain some of the complex and more difficult to understand mechanisms that drive an outbreak to a greater public. I'm not an expert in this field. I was thrown into it just like many of you. Lockdown in March, there I was trying to understand what is going on. So I encountered the work of Yanir Bayam from Boston and immediately caught fire, so to say. And I had to find out though that there is no information on his theory in German newspapers, so I decided myself to write something about it. And with the help of Professor Welsel and Professor Müller from the Department of Journalism, I got it published in Die Zeit. I think this shows you, if I may make this comment, how important the campus is, and please keep on coming, either here or at home, as long as we have to. It's a great place. It's one of the best inventions of human society, I think. Here it's about humans, it's about thinking, and if I may add this, the entire university, from Professor Garter, the president, down to the physics department, including also the follow of Professor Garter, Professor Manfred Bayer, handled this crisis excellently. Just, if I may say this, I feel very happy in this institution here. Well, let's talk about it. Let's see what we can do. What do you see here? Two soccer players. One of them is still, the other one was a player here in Dortmund. And you may want to ask the question, what do they have in common? They're both born on June 3rd. You might say, well, interesting observation, though, so what? Is this very likely or not? Well, there's another pair, a couple of players, same team, also born on the same day. Well, is this something special? Is this pure coincidence? So you may want to ask the question, how likely is it that something like that actually happens? Is it very likely, just a little likely? Well, if you don't know yet the birthday paradox, then enjoy this. If you have a team, two teams, soccer teams, 11 players each, plus the referee, 23 people on the field, the likelihood of two of them have birthday on the same day is 50%. I think this is a great demonstration of that human beings really do not have a very good intuition of probabilities, and I include us scientists. And physicists have to do a great deal of work to develop something like an intuition for probabilities. And the way we do this, the way we try to develop such sort of intuition is by dealing with simple scenarios, like throwing a coin, asking how many heads you're going to have, or what is the likelihood of having a certain amount of heads if you throw the coin n times. And you deal with this, or you actually find a formula. It's called a binomial distribution that looks like this. This says n factorial. There's this little exclamation mark. So maybe read this. I don't want to bother you with details here. If you go to large numbers, what you get is what you might know. Some of you in the Germans know it from their 10-mark bill. It's a Gaussian distribution, or the bell curve sometimes called. And what you see here is in blue is actually the regime, the probability that you find, if you throw the coin 100 times, that you find between 45 and 55 times head. Okay? So you throw the coin 100 times, and with a probability of 34 plus 34, which is 68%, it's between 45 and 55 times. If you keep on doing this, it's called the standard deviation. You increase the standard deviation, and you take the entire curve, including the green. It tells you what is the probability that if you throw the coin 100 times, what is the probability that you get between 35 and 65 times head, which is 99.8 times. What this is supposed to tell you is that the likelihood that some deviation from the most likely scenario, 50 times head, 50 times the tail, that you have deviations from that is quite narrow. So everything is centered, so to say, in some sense. Extremes are unlikely. Well, how is this in real life? Let's dive to real life. Let's go into a bar. This is a bar called Sligo's. That's back in the days from when I was living in Boston, in Somerville, one of my favorite bar, a little joint, nothing fancy at all. Let's imagine you just make a survey day, try to figure out what's the average incomes. And I'm pulling this out of my nose here, making these numbers up. Let's assume it's like $3,000 plus minus 500. 500 being the standard deviation, the plus minus 5, what I said before when throwing the coin 100 times. Well, sounds good. It means that between the probability that somebody earns a living between $1,500 and $4,500 in there is 99.8%, right? So you might ask, if you ask the question, so what's the probability that somebody earns money like, let's say, like $40,000 a month? You'd say, that's not going to happen. You're not going to find this. This is so super unlikely that you'll never find this. In this bar, one day, walks Mr. Bill Gates. And we know he earns a little more than the $3,000 plus minus $500. How much does he earn? I don't know it exactly, but it's somewhere in the ballpark of presumably, let's say, a billion or something like that. If you assume this, $1 billion a month. So now you have, let's say, 100 people that earn around $3,000 and one person that earns $1 billion a month. What's the average now? Well, if you do the math, you end up, let's say, with, 10 million. That's an average income of 10 million. So what is this number telling you now? The average income is 10 million. It just was 3,000. Mr. Gates has 1 billion. So what does this number mean? By itself, it's for this situation now a pretty meaningless number. What it means is basically that now you have a distribution in which one person, an extreme so to say, determines the properties of your phenomenology, whatever you look into. Let's say you want to know how much money is in this pub. Everything is determined now by the income of one person. If you want to, make a robbery of this pub, you are interested in one thing and one thing only, and is Mr. Gates there tonight or not? Because if he is, you're all set, so to say. Don't want to insinuate anything here, but just to give you an idea what I mean by property. So everything is determined by the extremes, and the majority doesn't matter, it's irrelevant. So it's basically exactly the other way around as of what we are used to think, of what we are used to talk about when we say averages, probabilities, how likely something is, and so on. It's definitely, it's quite the opposite. What's important seems to be irrelevant there, and what's irrelevant there seems to be important now. And if you directly compare those two, here in red, the Gaussian distribution for extreme events, all the way out here on the right, on the x-axis, then you see the probability, which is on the y-axis, is dropped almost down to 0. While for the Pareto distribution, which is the other distribution, I just want to talk about those two. There are many more, but I just want to put those two next to each other. You still, even for extreme events, have a fairly high likelihood, fairly high probability. And this is what is called, generally what you hear about is called a fat tail or the fat tail risk. And it's determined by a certain power. That's why these things are called power laws, but I don't want to get into the technical details. There's just two. I want to message here, there are two worlds of distributions. At least there are more, but I want to talk about those two. There's the one we usually think about, which is Gauss, and there's the one we usually don't think about, which is Pareto. So power laws or Pareto distributions are everywhere. They are, of course, known from Pareto, an Italian economist, who established the so-called 20-80 rule, which means that 20% of the population have 80% of wealth, something you have heard more often, I think, in the past few years. Pareto came up with this around 1900. But there are many more. There are US cities, there are word frequencies. I don't want to go through all of those. But since this is in the framework of a scientific series of lectures here, of the physics series of the University of Dortmund, I want to name one thing, because a lot of things we are doing in science is we try to measure it, which I don't want to comment on whether I find this a good thing or not. We count citations. So we publish and then we ask how many people have actually cited us. And in average, a paper, a publication you publish is cited about 3.2 times. And you would think, well, okay, this is an average, so if you want to hire somebody real good, he or she should have at least, let's say, 4 citations of her publications or his publications a year, right? But if you look in the data, what you find is that 35% of all publications are never cited. Another 49 are cited one time. So this is already making up 84%. By the time you're down at 4%, you're at 4 publications, you're down to 2%. So if you have 4 citations, you belong to the best 2% in terms of citations. This is how much the 3.2 means in this context. If you don't know the underlying distributions, it's meaningless. It's more than meaningless. It's confusing, and it leads to dramatic misunderstandings. So if you want to talk about probabilities of something, how many people are going to be dead and how likely it is that this is going to happen, or ICUs are overwhelmed or whatnot, you better know at least what kind of distribution is underlying the phenomena you're talking about. At least. It's not necessarily sufficient. I want to make one last relation. I want to try to understand. I want to try to tell you talk about the difference between those two things, those two distributions. The one thing, which is the coin throwing thing, is an independent thing. It doesn't matter how the coin threw today or this morning or yesterday. It doesn't matter for how it's going to fall tomorrow. It's irrelevant. The things are independent. And a whole another way of distributions comes out when the things are interconnected, like a chain. They're connected. They're not independent. If you make a distribution, you have a chain, made out of 1,000 individual links, and 999 of those links can hold a car. Then you say, then Gaussian distribution tells you this chain is going to hold you as well. Pareto says, well, the probability that this one link that you did not measure is a complete outlier, so to say, is not as unlikely as you would think. And of course, if this is an outlier that only holds 10 kilograms, it's not going to hold your body weight, you better don't use it. So that the stability of the chain is defined by one thing, an extreme. In this case, as we put it in day-to-day life, the weakest link. Extreme doesn't mean extremely stable, but it can also be extremely weak. So if you talk about these things, you need to know what distributions you have in front of you. So let's come back to pandemics. So what you see here is a map of Europe of the superspreader events. You see all those different events going on. You see the big one here in Italy in Milan, there was the soccer game where the people estimate about 7,000 people got infected as a consequence of this. Was one of the biggest, I think. So what is this? What has this to do with the Pareto distributions? You can map those distributions basically in this events in this distribution. So these extremes, the outliers, so to say, they are the ones who make the fat tail, so to say. And the further out they are, the more dangerous they are. So these are basically the super spreaders that you have in all kinds of levels. So it seems to be obvious what we need to do, isn't it? I mean, super spreader is basically, if you want, is a term that has been coined in 2003 almost to express the fact that in pandemics, the extremes, the outliers, the special spreaders, there are special types of spreaders, they drive the pandemics. It's not the mass here. It's not the mass here that drives it, really. So, of course, what we need to do, the conclusions, isn't it clear? Eliminate super spreaders. Isn't it crystal clear that's what we need to do? So let's do it. Let's eliminate the super spreaders. There is, however, a catch. There is a big catch, actually. Because you do not know what the super spreaders are from tomorrow. You do not. We doing, so to say, in some sense, an experiment right now worldwide where we find out quickly what potential super spreaders are. But the fact that you know some doesn't give you any information of how many you do not know. And super spreaders and all those things, these interconnected processes, these nonlinear processes, these chaotic exponential processes, they have something, they have something chaotic, they have something neurotic. And tomorrow a super spreader might come up. We have not thought about it yet. And if the weather is changing, if it's getting cold now here in Germany, and you go more towards inside, and the air is getting drier, and people changing their drinking or eating habits, sports, whatnot, things change. The virus has new transmission ways we have not under control yet, and all of a sudden you get super spreaders where you wouldn't have expected it. I mean, we think we know it's like soccer games, or it's like gyms and tight little pubs and whatnot, and wedding or birthday parties, and all of a sudden it's completely something else. And it's not it's like the Christmas tree factories, or it's like Christmas cookies, or it's like I don't know, something completely new, something you have not thought about. Or the schools that have done we think so well. All of a sudden something changes a little bit, and bang, it's chaotic. Slight changes have dramatic consequences. It's not predictable, and who tells you it is lies. Nobody really knows. We make simulations, and there are good people out there that try to figure out what potential super spreaders are, or what potential events are that drive this. There are serious scientists out there, no doubt. But we are not there yet. We're getting better. But we can do something. This is what I want to point out. We can do something before we have it controlled, before we have it understood. We can do something. We will have to do something anyways, but we can do something before, as long as we are waiting for the results, as long as we are waiting for the vaccine. We can basically eliminate super spreaders by eliminate infections. Having only few people infected will also eliminate the potential amount of super spreader events. If you have 1 in 1,000 of the infected people being a super spreader, well, it makes a big difference whether you have a few 100,000 or only a few hundred in your country or in your region, right? This will have a dramatic impact. And here let me visualize this a little bit. So what you see here is the so-called heat or fire map from Vincent Brunsch from Boston, who works close with Yanir Bayam. And what you see here is the heat map for Germany. On the y-axis, on the x-axis on top, you basically have all kinds of districts of Germany. Munich, Hamburg, Cologne, on the top. This is the map from the end of October, by the way. In green, green means that this district was free of infections. And y-axis, you have the day. So basically, you go to one day, let's say here, well, here's Dortmund, by the way, Schweinfurt, a city some of you might know out there. And let's go to June here, what you see here. So there's a lot of green in June. It means a lot of districts in Germany, a lot of Bundesländer, we call it here, where green were free of virus. Yellow means it's a single digit, which is mostly 1, 2, 3, 4 infections. So yellow and green basically means the virus was completely under control, or is, very little actions needed to be done to be completely safe, completely in the green. But there were a few spots left, a few domains here and there that would have needed a little bit more, let's say, stopping the fire. A few little burns, few little flames were still there that we should have killed, but we didn't. We didn't kill it. We talked on opening, getting back to normal. And as a consequence, of course, more and more super spreaders, and more diffusion of infection, of infected people happened, and more super spreaders came about. More and more clusters. And now, end of October, 2 weeks ago, we barely have any green zones. So all those all those green zones, we had to work for so hard to get them green, to keep them green, are now not green anymore, are now full of infected people again. This is the consequence. And what we need to do as a consequence now, as we are so closely to having a medical system that's overwhelmed here in Germany, and as you maybe heard in other countries around Europe, there's not much left than to do what people call the hammer, the lockdown or some form of it. I have not much else to add to this. Here's another way of looking at this. Basically see how the spreading takes place. So green means no virus. This is early in January of this year. And then you start, yellow means a few, 1 to 20, more and more are coming up. More and more are coming up. Getting darker means even more people. And here are we now going into lockdown. We kind of stopped the infection rates, going back to yellow and green. And as I mentioned, in the summer, we did actually pretty well in most of the country. We're doing all right here in June and July. A little bit more here, but we didn't. Instead of the lockdown, we started to reopening in the summertime instead of using the summer to kill the virus. And what happened, it spread it more, kind of from east to west, more and more. And, the districts, they can't keep themselves clean, so to say. The things diffusing in there if you do nothing against it. We did not, in other way, we did not protect and save the safe places. I want to take another angle on this same kind of problem from a field that is much more related to my actual research, which is phase transitions in biological systems or soft matter. And what you see here, let's imagine we have a two-dimensional ice water sheet, all right? And we have a few little fluid pockets in there, fluid little clusters. Now we drive the system close to the phase transition. Let's say this is something like what we maybe have after a lockdown. Not long after lockdown, but when we get the curve back down. So what you will see here now is actually a real simulation from a phase transition in a lipid membrane from my colleague Thomas Heimburg at the Niels Bohr Institute. It's a Monte Carlo simulation that really shows you how a lipid membrane is supposed to melt if you are close to the phase transition and now you increase slowly the temperature. So this is really a two-dimensional melting process of a lipid membrane, and what you see, you get more and more teeny clusters, and the clusters begin to grow, so you get new clusters and growth of clusters, you get more and more of them, and eventually you basically have flipped the scenario, and you have a liquid with some ice clusters. We started with the other way around. So the question is, what does this have to do with pandemics? Well, let's identify first the ice phase as not infected phase, and the liquid phase as the infected phase, all right? Now, the control parameter right now was was temperature for water. What is the control parameter in a pandemic or in an outbreak? Well, the closest thing I could get to is something like what I call the connectivity, or what many people call the connectivity, and you use this word kind of loosely here. The idea is, you may ask the question, what does temperature actually do? And one simple answer is, temperature is increasing the probability that you switch from ice to liquid. So the question is, what increases the probability to switch from non-infected to infected? And this is I'd like to summarize with the word connectivity. Of course, there are very many little mechanisms that go into this one word, but it's like connectivity on different levels, like in your household. And how do you spread it in your household or in your little local neighborhood with your friends and so on? How do you spread it among work, like in a larger community? And how do you spread it on a more like global level with transatlantic flights and then long train rides and whatnot, where you really cross a lot of distance? Okay. So I just thought it might be helpful to see that there is something that all of a sudden the whole thing flips quite dramatically if we don't watch it, and we might not smell the transition. We might not smell the point, that outbreak point. And I think I'm afraid we didn't for the second time. Well, you might ask the question, well, this guy is standing there telling me something about Pareto distributions and phase transitions. Well, did I really want to know that? You probably came here because you thought this is about something that's important right now for many people. So the question I have to face at one point, of course, I at least have to address it. Is this really dangerous? Because what I'm talking about here, like the way infections spread and all those dynamics and this power law distributions, this is also correct for athletic foot disease. So this, for any kind of fungus that, can be transmitted from from person to person. But would you really come here if I talk about fungus that can spread? I don't know. Well, so yes, how serious is this disease? And well, I'm not a medical doctor, and I don't want to pretend like I am or I know as much as them. I just want to look at it from a different angle, namely from the angle of there's no doubt this is dangerous. And the scenarios in Bergamo, in Italy, in Spain, in New York, or of course in China, have shown us this can be a monster. This can be bad. And even if we claim that most cities or most countries have done well, we have to face the fact that in pandemics, in interconnected phenomena, we have to focus on the extremes to understand it, to get it under control. They will manage, they will make the final outcome. 16,000 people, roughly, died as a consequence of this one outbreak in Italy. One scenario, one event made 16,000 people. So if you take this away, almost nothing happened until like, let's say, I don't know, March or April. Then more and more people died, and now it's 40,000. But still, one event was so dramatically important for the overall outcome, what's going on in Italy, that we can't neglect it. Because it's not athletic foot, it's dead people. And the second note I want to make is that there are potential side effects, and I want to compare this like if you have to decide to take a pill. You have to take a medicine, or you don't have to, but you actually, you take it for something, let's say, get a good night's sleep. You want to definitely look into what are the potential side effects, even if it's anecdotal, even if the company tells you, we have seen this every now and then, but not often. Even then, I think I would recommend you to be somewhat skeptical and weigh out how important it is. And then there's the other discussion about all the risk groups, so-called risk groups. It sounds like there are these few people, these few hundred or few thousand people in Germany, we have to bring them in a separate room and make sure they don't get it, and that's it. And that's all. Well, if you add up those numbers, at least in Germany, you easily end up with 20, 30 million people. And if you take the ones under 25 away from this, because you're really saying, okay, they are quite safe, so you only count people 25 and older, this is 60 million, and 20 to 30 million of this is every third to every second person. So 30, 40, 50% of our adult population is part of this risk group. This is not a little minority that we have to watch out for there. So let's face it, many of us, and please don't worry about it, many of us feel uncertain about this thing. Are we a risk group? Are we not a risk group? Are we over-worrying? Are we not over-worrying? Should we have this kind of restrictions, or should we just go on with our life as if nothing is going on? We are in an insecure place. We are living with this uncertainty. Let's face it, and it's all right. But I want to give those who sometimes are called you cannot just lock yourself in the basement and be scared at home all day. I want to give them something to support them. Don't let them tell you that. The precaution principle makes total sense in nature, and I think you find it a lot in animal kingdom. Precaution principle makes you survive. It's evolutionary, Darwinistic, so to say. So if you take this from Nassim Taleb, if you are in front of a stone and you mistake it for a gorilla and you run away, it might be embarrassing, but not harmful. But if you are in front of a gorilla and you mistake it with a stone, it might be very harmful. So you better watch out. And if you're not sure if this is a gorilla, or if this is a stone or a monster in front of you, this is pandemics, and you're not 100% sure if are you a risk group or not, apply the precaution principle. Be careful and sit it out. Be careful, mask, double mask, avoid certain situations. You don't need to panic. Just be careful. It's two very different things. I want to come in the remaining time back to something I mentioned in a little bit more detail, which was I was talking about that things change as we go into the colder season here in Germany, and this will create new, let's say, opportunities for the virus to appear as a super spreader event. Gives the virus new ways of, super spread. And I want to talk, because of that, a little bit about transmission in rooms, and I want to talk about transmission in general, a little bit of aerodynamics of virus transmission. So what you see here is the work from Yang and Stone in a fairly recent paper that try to visualize the droplet that comes out of let's say, of a human while speaking. And what you see here on the left, or let's imagine on the left, what you see, the left person is an, let's say, asymptomatic infected person. On the right-hand side, you see somebody that's breathing in. And the question is now, how much virus are you actually breathing in if this is an infected, asymptomatic person a certain distance away from you? And first, you want to keep this simple and short. First of you breathe out a certain amount of air. This is the A times V term. And a certain amount of this, again, then are droplets. So they have a certain amount of droplets you spray out. They distribute in this funnel-like shape, which is also called a turbulent jet. And so the concentration goes down a little bit as you move from the mouth of the infected person towards the receiving end, so to say. If you use momentum conservation and particle conservation, so the fact that, that you have that all the momenta, all the little collisions are maintained and no particles really disappear, they just spread and funnel out like this. If you keep that in mind, you can calculate the inhaled virus load. So what you see here is in CV, the CV is the concentration of virus in the droplets, R is the amount of droplets in air, so to say. The X is the distance between the two guys, Q is the breathing rate, and T is the time. So you need to know all those numbers, but we have all those numbers. We also have the angle alpha, and we have the size A of the mouth, and we can plug in those numbers. But let me tell you one first result you see from this. You see that the number of particles that you inhale, this is N, is proportional to time divided by distance. So the longer you wait, the more particles you're going to inhale, and the further you go away, the less particles you inhale. So, however, we want to get to do some real numbers. And for this, we plug in a couple of numbers from literature. I have them here. I don't want to go through those. I did not measure them myself. I just basically plugged them in here. And if you do so, if you plug all those numbers in, then you get the numbers of particles that you inhaled is 0.3 times time divided by length. So this number, the 0.3 that you see here, is of course, it's really just an estimate. Order of magnitude, it can vary quite a bit, and it's only meant for asymptomatic patients. However, I would be quite surprised if this number turns out to be 1 million or something like that. The superspreader, for example, will create a lot higher number. Superspreader, I mean now from the perspective of like how infected the person itself is. Like, it's not an asymptomatic person anymore. For example, a person that has already a 40-degree fever or 102, 104 fever, something like that in Fahrenheit. Anyways, if you now apply this quite simple formula to, let's say, a 5-minute conversation at a distance of 1 meter, you get a number of inhaled particles of 100. So you might want to ask the question, what does this actually mean now? Well, first of all, it's a rough estimate of the number of inhaled viruses that you got, but what does it mean? Isn't one virus enough to get infected? Or do I need 1 million to get infected? What are the real numbers? This is not totally clear. This is actually a pretty big problem that we are addressing there right now. In generally, the way this kind of idea is approached is the so-called dose-response curve. That means the number of, it's also we know this from medications, the number of drug or the number of virus you take up will determine the response, and this response curve is not linear. It's actually often highly nonlinear. It's like it has a threshold, meaning under a certain point, you take a certain dose and nothing happens. You double the dose, still nothing happens, and you triple the dose and everything happens. This is just an example, just to give you the idea of what I mean by highly nonlinear and threshold. There's underneath a certain level, there's nothing, and above it is everything. But we don't know this curve. I'm just telling you what we expect, what we expect to deal with. So what we would need to know, of course, if this is true, where is the threshold and how wide is the threshold? If we don't know this, then it's hard to say what 100 virus inhalation actually means. Is this dangerous or not? How do we move ahead from here? Well, if you talk with a virologist or a medical doctor, at least as far as I understand, at least 2 things are very problematic to get to this number. First thing is the experiment is incredibly difficult to do. Imagine you want to find out at what threshold a person is infected. You basically need to expose this person day by day with viruses and see what happens. I don't think this is morally or ethically something that you can or should do. On the other hand, virologist tells you this is not all, this is already difficult, but there's more. And this is that these numbers are individual. This means they vary from you to you to you to you. They're not the same for everybody. And one obvious thing might be that seemed very plausible for me is that's like your mucus in your mouth and your throat. Your mucus is different, and the mucus protects your epithelial cells, which get affected eventually. So if you are living in a dry climate, or if you are in a dry climate, or it's winter and you spend a lot of time outside, or you're somewhat troubled by a cold or something else, and your mucus is not in perfect shape or in good shape, you might need a lower dose. And there are other more like direct physiological reasons that might make this individuality, the way your immune system responds and so on there, and the way your epithelial cells respond to a virus. So there are many different ones, but this seems to be an obvious one. And it adds to the problem of like figure out, but can we do something? Is this all I have to say about this, or is there more? And physics helps a little. There's a number of observations that people got infected in restaurants. And this is one famous one that has been studied a lot. It's a restaurant in Guangzhou in China. And in January 2020, there was a little superspreader event. And you see in the front here, this person in pink here, number A1. He was infected, as has been turned out, and he was asymptomatic infected. But what they found in these restaurants is that people far away on another table, not related, this was not a group, this was not like a big party, it was just people going to a restaurant and sitting on different tables. People like 4 or 5 meters away got also infected. You see those in red, all those in red are infected. Like let's say C1. How can C1 get infected if they never talk to each other so far away? It has to be by indirect infection, meaning through kind of the aerosol, through the air, not by direct communication. So we are dealing with indirect aerosol infection. For this, we need to understand a little bit of the physics of aerosols, and here Professor Roland Netz from the FU Berlin, Freie Universität Berlin comes to help. A colleague of mine studied and published with for many years now, and he basically has made a very nice theory about what actually happens with aerosols when they leave your mouth and how dangerous they are to infect you. So basically, I'm here, or let's imagine I am an asymptomatic infected person. I'm here, I spray out, I produce little droplets. The big ones, they fall to the ground. The smaller ones, they get carried. So I keep on producing them, the room gets filled with more and more of these little particles, more and more sediment out. Eventually, the number of particles that I produce and the number of particles that disappear will be about the same. And the way you deal with this is by so-called differential equations. What you see here, the first term in the differential equation, the F drop, is basically the production of droplets. M is the number of infected people in the room. And then you have two terms for loss of little infected droplets loaded with viruses, namely by sedimentation and by ventilation. So if you take this into account, eventually you get to a state that the number of particles or the number of droplets in virus, therefore, you produce is the same as the number of droplets that you lose. Meaning you have something that we call a steady state. So there's a steady state of the viruses in air, and Professor Netz finds two expressions for that, or gives two expressions in his paper, namely one for no ventilation, the upper one, and one for with ventilation in this room. The F, air, is with ventilation. Either way, the number of this a number of viruses in air in steady state is not that easy, and the reason why it's not that easy to calculate, there are a lot of easy terms here. R naught is just the initial size, M the number of people, F drop, the rate of droplets that you can measure, C virus, the concentration of viruses per droplet. But what's hard to measure or hard to get a grip on is tau Z, the sedimentation time. Because this sedimentation time depends on a number of things, and what Professor Netz describes in this paper. And it's like the droplet first comes out of your mouth, it begins to shrink. Because it shrinks, it gets smaller, and the sedimentation time goes down. This seems obvious, but while it shrinks, the concentration inside the droplet increases. You see this in this little cartoon, the blue droplet with the red solid particles in it. As the droplet shrinks, the concentration increases because only water evaporates, not the solid particles evaporate. So you concentrate your proteins, your viruses, all the solid particles. And this leads eventually, because the particles want to keep the water in there, this basically leads to changes of the osmotic pressure. The vapor pressure on the droplet surface goes down, which is basically a symptom for that the evaporation rate goes down. So the particles stop to evaporate. They stop to shrink, more or less. So they reach a certain size. Okay, what Professor Netz then did, you multiply the time, the sedimentation time, with the size of the particles, because you want to find out what is actually the most dangerous distribution of particles. And this is, the bigger, they have more viruses, but they sink. The big ones that also take a long time to settle down, these are the dangerous ones. So to multiply the sedimentation time with the volume is actually what's really gives you the particles that you want to avoid. And there he finds this is the particle size 5 to 50 microns. And indeed, if you take something like 20 microns as the initial size of particles, you find, or you vary around this a little bit, you find a viral concentration in steady state, a number of viruses, not a concentration, of 10 to 100,000 in air. And if you apply this to the volume of this restaurant, which was about 40 cube meters, and the typical breathing rate we mentioned before, you end up with a couple of viruses that you inhale per minute, or that person C1 in the picture before inhaled. And a couple of viruses, like let's say 2 per minute, means about 100, 120 per hour, and the person that was given by this person, the customer in the restaurant, C1, was in there for about an hour. So he must have inhaled about 100 viruses, if this theory is correct, and he got sick from it. He got infected. So 100 viruses can be enough. That doesn't mean that less can be enough. It also doesn't mean that it is always enough, no. But a few people got sick and they all had to inhale this order of magnitude of particles. So somewhere around 100, there's a number where things get iffy, for many of us at least. So this is supposed to show you a little bit how physics can help here. But of course you can protect yourself. You don't need just to sit around in a restaurant and inhale. You can wear a mask as good as you can, of course not while you're drinking, but yeah. Wear a mask where you can. Masks are super potent helpers, super potent killers of the pandemic. They're so easy and so cheap. It's almost hard to imagine why you would not use them, maybe including for a flu season. So and of course you filter in and out. You filter both ways. So if somebody would, like without a mask, throw out 100 particles, and it's filtered, let's say, by roughly 1/3. So only like 33 particles make it through the mask. And the second person, the receiver if you want, also has a mask. It filters another 1/3. You get only 11 particles from the initial 100 ones. So you filter with the square. This is a nonlinear effect, and this is so important that these are all multiplicative effects. So if you summarize, the number of particles that you inhale is some constant times time in seconds, meters in length, times p squared, where p is the filter factor of the mask, like around 1/3. And you can plot this, and what you see here is the inhaled viruses with no mask, the inhaled viruses with mask, one mask, and the inhaled viruses with both people wearing a mask. And what you see is you get from like 120 particles without a mask to 40 with one mask to 13 with two masks. And this cannot be underestimated. This is already almost a factor of 10 that you reduce it. But think about what I told you before, that there is probably a threshold regime. And this scenario, wearing two masks, might kick you from highly risk to low risk. Not just a little bit less risky, but it might almost kick you from really high risk to really low risk. I don't know this threshold exactly, but we do know 100 is a risky regime. I think this seems to be fair to say, and several other studies have produced similar numbers. And also, I want to close the mask story for here, at least. It also was shown in this fairly recent Nature Medicine paper that it seems to reduce the number of viral load in aerosols. So they were basically not detectable anymore in this study, the viruses in aerosols, when the asymptomatic infected people had a mask on. So this might be something also I have to think about it in school classes or lecture halls and things like that. Anyways, wear a mask. 1918, Spanish flu, even the cat wore a mask. So if a cat, why can't we? I want to close. I want to ask the question, what do we do before the next wave arrives? What are we going to do if we are over with the wave? So let's assume now we're going into some form of lockdown. We are making sure the stuff's not exploding in front of us. And then we are in this kind of scenario. So we have infected, but it's like manageable. Are we going to reopen again everything and loosen everything and like go through the next wave until something magically happens and it's all over? Or are we going to change and try to eliminate the damn thing so that we can live a normal life again? Also supporting, of course, vaccines, because they're not going to be here just like 90% are going to be immune overnight. No. We're going to help the vaccine, and we're going to support it if the vaccine is not perfect or can't be produced quick enough or has side effects or it doesn't work for certain populations. We're going to support all those effects. The vaccine is an additional factor and shouldn't be seen as just like the one single major silver bullet. There are concepts and models out there. The green-zone model, of course, from Yanir Bayam, and the Swiss cheese idea that I want to present here from Thomas Pueyo, also the author of the Hammer and the Dance article. So you imagine you have your zone gotten green. You have the numbers down. You managed to get them down. How do you keep them down? Well, you make sure you try not to let too many infected people go through your first line, or first firewall, your first slice of cheese. Let's say you filter 70%. Then you have your next slice. That's like, let's say, like putting some restrictions on mixing of people, like big events and like lots of big gatherings of many people. You restrict this. Then, of course, you enforce masks and hygiene as much as you can, even also in rooms, the way people are in supermarkets. Limit the number of people, of interactions, and so on in there. And, of course, if the numbers are low, you probably have the capabilities, at least in a country like Germany, you have the capabilities of testing, tracing, and isolating people. Okay? So if you do all this, because it's multiplicative, you eliminate easily 99% of infective people. You don't need to get them all in one shot. We should try the better, of course, but you don't need to get them all in one shot. And if you do that, like the Asian countries have done it, or like New Zealand has done it, or like Australia has done it, we might be coming back to some sort of normal. And this is not just like you can say, now these are isles. No, well, that's not the point. If you can't protect the borders very well, let's say you only eliminate 30% at your borders, well, then you got to do a little bit more on the other ends. So you end up with the same number, eliminating 99%. And this is something we can deal with because you basically have to multiply this number, well, you have to multiply the 1% with the R value of 3 that you typically find in this corona spread. Well, I want to finish and tell you, take care of yourself and your fellow citizen. And mask. You get them in all shapes and sizes. No problem to get them. So that maybe next time, when this wave is over, when we have flattened the curve, when we have brought the numbers down to something bearable, we finish this goddamn thing and get back to normal, like Dortmund, listen, back to soccer stadiums. And if you go to the pub, please, if the pubs reopen, please wear the mask also when you order. Solidarity and for your own protection. Solidarity with the waiters and waitresses. I want to finally thank a few people, namely Janir Bayam, for this inspiration. I wouldn't have done any of this without his ideas. Vincent Brunsch, who fed me a lot of good data and the heat maps and all this. Gregor and Andreas, who helped me a lot for shaping the data, and my research group, who gave me enough space to work with it. The physics department, they let me do this while I'm here. And of course, I want to thank my family that have suffered a lot. When Daddy always talks about corona. There's certainly nicer things out there. So I send you a big hello from the campus, Dortmund in Germany, out there. Stay safe. See you soon. All the best.
Professor Schneider now answers the questions he was asked in the online discussion after the original talk. Did I understand correctly that masks work not only to protect others but also yourself?
Yeah, I never quite understood that, why masks should only work one way, because obviously they filter in both ways. Of course not identical, of course this is not a symmetric process. I mean, you already seen when you talk, you have this turbulent funnel-like jet, and when you breathe in, you get this hemispherical like airflow, which probably creates different forces. In so you would expect asymmetric filter factors. This is no surprise. But having this said, of course, they should work both ways. Maybe as we are talking about masks, we should maybe mention a word about face masks. If they're really good, they can actually work pretty well as well. Really good. We probably should look up in yourself and ask. But they should cover your chin. They should be close, seal your forehead, and go to your ears and stuff like that. So not just a little thing that covers the nose. So I think that's good. But there's one thing there seems to be, at least in Germany, there seems to be a confusion out there. I was in a sandwich store the other day, and they have hanging there a little like plexiglass shield, and behind are the guys without masks, and left and right there's nothing. It's just this little shield where they give you the food, and it's because this is near to useless. I would say, if you should sneeze right against this, it might be helpful. But apart from that, it seems like I cannot recommend this, I think.
Could you elaborate on your conclusions from the observations on cruise ships, masks, and severity?
I'd like to repeat it. First, maybe I wouldn't say I have an explanation, but the conclusion seems super clear. So basically, you say that and you're not either infected and in the ICU or you're infected and you're sitting at home watching TV, but there's a lot in between how severe your state is, state of illness. And there you have this nice experiment, I'd say from a scientific perspective at least, because you have an enclosed, well-defined environment on a cruise ship. And you had this early cruise ship in the Princess Diamond where you had, I think, around 500 people infected, and 18% of the passengers were asymptomatic, so I had no issues at all. There were no masks, or very little. And then was a few months later, I think in the summertime, there was a cruise ship from Argentina where people responded quickly and the crew handed out masks when there was the outbreak, and people who treated sick people were especially equipped. And they're still under the infected people. I don't even want to talk about now how many people less or more got infected, but under the infected people, about 100 I think if I remember, 80% were asymptomatic and 20% symptomatic, so the numbers were reversed. So basically the conclusion is, because this experiment is very well defined, the conclusion is that the main difference between those two scenarios were masks and no masks. And this reversed symptomatic versus asymptomatic ratios. So the conclusion is that masks not only help you getting not infected, but if you do get infected, they reduce the virus load and therefore the severity of your illness. So that's basically the idea. And maybe a little anecdote that I've heard also from Nassim Taleb in this context is that because we're talking about boats, a little bit off topic, but still interesting, I think. Even back in the days when the ships would come from far away to trade in Europe, let's say in Italy, you're talking 1,000 years ago or more, when there was the slightest indication that one of the people, one of the crew on the boat is sick, they would have to go in quarantine for like 40 days on an isle. And the people who ran the boat, the people who owned the boat, they actually knew that this could happen and had it as part of their calculations.
If droplets sediment, aren't little kids playing on the floor at higher risk for smear infections?
I think all I can say about this is that basically most of you already know. It seems like that smear infections don't play a major role. I think that was the state of the art, and in March, April, or this was what people have been mentioned more and more back then. I found lots of indications, and I have heard no contradictory results since then. So I still think it is strongly believed that smear infections play only a minor role, if at all. Having this said, it's of course a different story if you have little kids crawling around on the floor and having their hands everywhere. I think there we should don't just trust in me. Go to your pediatrician and discuss that with them. No, that's a different story.
During a phase transition in a homogeneous fluid, how do you imagine a heterogeneous distribution, i.e. superspreaders?
Yeah, the comparison is not perfect. Of course, always have limitations, but I think it demonstrates the phase transition that it's like this very dynamic and powerful process that you get from one harmless state to another state very rapidly. It's like changing some parameters only a tiny bit, like the temperature and phase transitions. Having this said, I guess near critical points, power laws are the thing, and I do believe that the domain distribution, at least in some phase transitions near critical points, the size of the domains, I think it follows a power law. I think so you do get heterogeneity, you do get power laws near phase transitions. So this is not, but the comparison, of course, has its limitations, but I think it captures some of the features of the transition from non-infected to infected, so to say.
How do you get to the numbers mentioned in your Zeit article, that 1/1000th of events determine more than 30% of the properties?
Yeah, the question about that, where the numbers come from, I mean, it's a good question, but in principle, it's like empirical. So Pareto found the 20/80 law. It was an empirical fact. I mean, that's just the way it was. And then from there you go down to smaller numbers. To like, what is the probability? What is how many make 30%? How many make 50%? So on. You go down by keep on doing that, because it's a power law. It means it's scale invariant. It means like you have 20/80, and in that 20 you have another 20/80 and another 20/80, and then you go down to until you end up with 0.1%, and then look how many percent this 0.1% is actually be responsible for. So that's or earns whatever. So, and it looks like, if you go into empirical analysis, it looks a lot like that. The exponent, the powers are very close to Pareto powers. I think the general trend is that the tails are a little fatter even, so the meaning that you get rather a 10/80 than a 20/80 kind of distribution. I think that's what people think. So 10% of the infected made 80 of the newly infected. So this is our stand, and once you have the empiric, what Einstein would say, the empirical, a certain thermal behavior straight, you can look and get more and more confidence, and also looking at it from the model perspective, and at least a simple model that gives you somewhat of a feeling what's going on is when you have two exponential processes, you combine them, you get a power law. So for example, if you have if the probability that some infected person shows up in your region is increasing with time exponentially, so the longer you wait, the higher is the probability exponentially that some infected person shows up, a nucleus, so to say, as we would say in the field of phase transition. And at the same time, the growth, nucleation and growth, the growth is exponentially as well, and you get a power law for a very simple reason that the probability to get early infected is low, but if you do get early infected, you grow large, So you have few large clusters and some small ones, lots of small ones. So that's, you get kind of a power law if you combine two exponentials, and the power you get from the ratio of the rates between nucleation and then the local growth process, so the global and the local growth rates. So this is and I think now, if you have heard, I hope if you have heard this presentation and this little discussion, it shows like how absurd it is in the ears and brains of people who understand this a little bit. If people compare this with the probability of getting a heart attack, for the very simple fundamental reason, a heart attack is not infectious.
How should we approach people that ignore or deny the risk and measures of COVID-19?
Good question. If you remember my very first slide, I had the phrase, when you mix science and politics, you get politics, from John Barry in a recent New York Times article. And I don't want to mix it too much, but I'm married with a American psychiatrist, so if I don't say a little more about this, I'll probably get my butt kicked at home. I'm just kidding, but these people, or many of those people, if not all of us, are in a state of uncertainty, in an insecure state. And in such an insecure state, very often people rush to authority without testing if this authority is really a reliable authority. Rather, you pick authority by what you want to hear. You're anxious, you don't want to even admit to it. And somebody says, well, that's all a whole load of hoax and bogus, so don't believe it. Everything is fine, you don't need to worry about anything, and that's just what you want to hear. And I think this is where you have to meet the people. We are all in a state of uncertainty. We don't know if we should invest in a pub, open one up. We don't know if we're going to be able to pay the mortgage, So we are in a state of uncertainty, and we have to appreciate that. And I think this is where you have to meet the people. And when you get them a little bit to open up there, you have to come with your arguments. You have to try to establish trust. So give them some, hint them to some people that are trustworthy, hint them to some newspapers or papers that are trustworthy, that write both sides. They don't have too many horses in the race, but they actually write honestly. There are people out there in Germany. There is, of course, first of all, Trosten, who is really excellent, and there are good papers out there as well. And I think without trust, it's hard to get through such a crisis. That's hard. So see where the people are, meet them there, and establish trust. But get them to read things that might not always be very comfortable, but they feel like they're true. They're honest. All right.
What do you think about the often mentioned trade-off between health and economic damage?
Yeah, the so-called trade-off between health and economy. I think it's a false dilemma, mostly. Not necessarily at all circumstances, but especially at the beginning. I don't think you find anybody. I think you don't need a PhD in physics, in medicine, or in economy to realize that if you stop the fire early, it's the best you can do in any perspective, from any perspective. And if you have to sacrifice 0.1% of the economy to save 99.9% and a lot of lives too, of course you do that. What a question. Unless this 1%, this 0.1% is a very strong lobby, then you might act differently. But this is politics. This has nothing to do with science. Scientifically, it's crystal clear. Also from an economy, scientific, from a science, from an economic perspective. So, and the fact, it speaks for itself that Peru, Spain, and the UK are the countries who suffered the biggest losses in their GDP compared to last year's second quarter, is more than 20% loss, but have the highest amounts of death per capita. What else do you need to know? And this in Europe is so often discussed Sweden model, of which I'm not so sure how many Sweden like the fact that it's called the Sweden model. But you also should pull out the facts. The motivation was like the economy should keep on going, and it's not going to be so bad. The economy in Sweden is 3 or 4% better, so suffered 3 or 4% less than in Germany, for example, but 400% or more death. Right up there with the United States under the administration of Donald Trump. I don't know if this is the type of model that I can recommend.
What measures would you propose once the lockdown is over?
Well, about measures, go to Yanir Bayam's homepage and coronavirus.org, as very well described there. But in a nutshell, it's a green zone idea. So first get the numbers down, so that you actually know what's going on, and then try to keep the green zones green, to stable the low numbers, keep them stable by not letting people from the red zones easily spread out, and make sure you also keep the boundaries, the borders of the green zones somewhat clean. So make sure not too many people come in, and if you do both, it's multiplicative. It's very powerful. But of course, you might not be able on a country or state or whatever level to keep your borders protected. They are leaky. Of course, you don't want to live in the world where you're not free to go anywhere anymore. So you need additional measures, and this is where the Swiss cheese model comes in, from Thomas Boyeo, the same guy who wrote the article on the hammer and the dance. So you have a second layer. Some people come through the border checks infected. Then you have the next measure, like you don't allow all kinds of mixing. You limit the mix of people, how many people mix and interact and collide and spread socially. Third, you have a third layer. Still people come through, which is the face masks, hygiene, and so on, all those kind of measures, good ventilation in rooms, having rooms set up in a certain way, only have half the people working in certain shifts and whatnot. And third, you have, of course, the layer. Fourth, you have the layer, of course, contact tracing, testing, and isolation. If you have low numbers, you get that under control. If you have overwhelming numbers as we have it right now in Germany, there's no way. But if you have low numbers as we had them in the summer, you get control over it. You know what's going on and where are people who are infected, and then you can actually trace back and identify where those infections came from. And you have two things that happen there. First of all, of course, you catch much more, and second of all, don't forget, we have to look at the extremes, the superspreaders, because 10% are responsible for 80% of the people that you test positive. So we first of all, we catch much more people and know where they are and can isolate them. And second of all, we learn about what potential superspreader events we don't have on our radar yet. So we will learn about that too, which will be very important in the long run. So both those, all those things together are multiplicative. And if I can only repeat this is one of the crucial points of understanding. At the growth level, it's multiplicative, it's exponential growth, but also the way you can kill it, to kill the virus, eliminate it, can also be multiplicative. So go and bring the numbers down and then keep them stable down until the vaccine comes, and it will help. It will accelerate the power of the vaccine. We will need much less vaccine. We will be much quicker safe if we have low numbers. Don't just expect everybody is infected and you just get the shot for everybody immediately. No, it will help. Even if the vaccine comes, it will still help if we have low numbers. So I think this is a very important realization. But finally, I'd also like to mention an idea that I published in the Zeit article, that you should make this more attractive, and you can make this more attractive. So making it attractive to keep the number low. Don't make it not attractive. Don't do the opposite. Don't make it attractive to always get as many infected as allowed. No, make it attractive to keep the numbers low. So that red zones want to become a green zone. So you have a rush towards the green zone. By for example, by giving green states more freedom, or any kind of incentive that you want, so you get a rush towards green and not a rush towards red, as we had at least in Germany this summer. So make it attractive. So we go down in numbers together, and once you get those numbers down, like in the Darwinian process, basically an idea that I stole from Manfred Eigen's idea from selection. You instead of saying like you have to be below 50, no, you have to be below a certain average. And only if you're below the certain average, you can like loosen up and you get your incentives. So now you're in the red zone and you try your hardest to go under the average. Okay, you actually, as the red zone that tries hard to get green, you bring also the average down, which drags other states, other communities down as well. down to lower numbers, down to lower infection rates. So you have a suppression of infections instead of a rise. You have a suppression, and then you stabilize it, and you use all those concepts of the Swiss cheese and so on. And I'm quite optimistic that it would work just as it works in the Asian countries and in New Zealand and many other countries. Of course, you can't do it identical. You know, we are not an isle. We are in the middle of Europe here, but then we have to be a little bit more consequent on other screws, and we can do that. We can pull it off, I'm sure.
What do you think about mass testing?
Well, I don't really want to say or can't say much about mass testing. I leave that to the epidemiologists. They should address that. I'm sure it's interesting, but you know, I should refer you to those scientists. But what I can say is that a clever testing system, fast, inexpensive, and with good supply, of course, is of course a major weapon in battle the virus. You know, you've seen in the Swiss cheese model that you have several layers. You know, you have leaky layers, so to say, where a certain amount always kind of gets through. And one layer is, of course, an important layer is testing. I mean, if you can, I mean, you don't want to keep your borders like protecting in the sense of from a nationalistic point of view, of course. I mean, you want to give people a chance to come in. We don't want to, you know, fall back in that kind of nonsense. So, and having a lot of tests and quick tests and cheap tests, inexpensive tests available will be, of course, a major improvement there, and then stabilize that slice of the Swiss cheese that filters at the borders, and that helps tracking people down, tracking the source, the superspreader went down, the origin of many, which, you know, as you know, the origin of 80% of the infections. So yeah, this is a weapon that we should use to get this under control. And also, I guess we will probably need it eventually if we want to get to bigger gatherings again in any time soon.